Welcome to this video in which we introduce the concept of a free body diagram and show a process by which free body diagrams can be made. A free body diagram is a sketch of an isolated system of interest and the external forces that act on this system. For our purposes, we'll assume that the system is closed, which means that matter does not go into the system or come out of the system, so we have a fixed collection of stuff. Every atom that starts in the system ends in the system. And for this, for mechanics at least, the measure of interaction is forces. So the system that we're interested in will be interacting with the external world only through forces, basically through forces and moments. So on the screen I've drawn the process of creating a free body diagram, and so what I'd like to do is go through this process with a simple example. So step one is to define the system or the body. So let's go to an example. Okay, so here we have a cat, and the cat is walking out on a beam towards that pile of green stuff. Let's assume that the pile of green stuff is catnip, which for those of you that don't know, cats really like. In fact, it's almost like a drug to them. The beam is supported by a brace and is attached to, both the brace and the beam are attached to a wall. And what we want to do in this example is we want to draw a free body diagram of the cat. So we will define our system to be the cat. Okay. We will not consider our system to include the catnip or the beam that the cat is walking on or the brace or the wall. Our system will be just the cat. Okay, so that's step number one. We've defined our system to be the cat. Let's see what step number two is. Step number two is to sketch the system. Basically, the idea here is to sketch the system in isolation. And rather than actually draw the cat myself, which I'm sure would be entertaining but probably ugly, I've just copied this picture of the cat. And we'll have this picture of the cat represent our sketch of the system. Now we typically, well, you'll notice that in our sketch of the system, we're not including the beam, we're not including the brace, we're not including the catnip. All we have is the system of interest, which in this case again is our cat. And typically when we draw this system, we are interested primarily in the shape of the system and not of the internal workings of the system. So in this case we haven't drawn any parts of the skeleton or any of the stuff inside the cat. Okay, so that's part two, is to sketch our system. Step three is to determine where has the system been cut from its environment and where is the center of gravity of the system, or components of the system if you want to work with those. Okay, well, our system has been cut from its environment on this paw, and let's assume this paw. Let's assume those are the two paws that were touching the beam. Everything else the cat wasn't touching, no other part of the cat was touching anything. So these two paws would be the points where the cat, or our system, was interacting with its environment. Okay, you'll notice that we will not consider the catnip. The cat may have been moving towards the catnip, and in that sense you can think of it as interacting with the environment in the sense that it's decided it's going to go get the catnip. But in terms of our free body diagram, the cat is not touching the catnip. The catnip exerts no force on the cat, no physical force. Again, it may incite the cat to move towards it, but that's not a physical force. It's not, the cat's not moving towards the catnip because the catnip has some mysterious force that's pulling it towards it. Okay, so we've defined then the points of contact between the cat and its environment, and let's assume that the center of gravity of the cat is right about here. Okay, so basically now we've completed step 3. So if we go back to step 4, we now want to represent interactions between the cat and its environment with forces and torques. Okay, so if we go back to the cat, one force that we will need to include is the force of gravity. Okay, so we'll assume that this force operates from the center of gravity, so we might call this force W. Okay, and gravity typically in mechanics is the only force that you consider that acts at a distance. There are other forces that do act at a distance. For example, if you've got an electromagnetic system, say a motor, then there could be magnetic forces or electrostatic forces that act across a distance. But typically, unless you have that sort of thing, gravity is the only force that you tend to take into account. And then we also would have the beam producing forces or interacting with the cat with forces. We might call this force FA. And we might have a second force FB. Okay. And the idea here, again, is that the way the cat interacts with its environment is through forces. And in the free body diagram, we're interested in those forces that are acting on the system. In this case, we're interested in the forces that are acting on the cat. So, in this case, what do we actually know about these forces? We would know that gravity is pointing down. We actually probably wouldn't know, if we know the mass of the cat, we could probably figure out what the force of gravity would be. Without some further analysis, we would not know what the force A and force B are, both the magnitude and the direction. Now, one of the things that you'd be tempted to do at this point is to start applying your knowledge of statics or dynamics and trying to figure out what these forces are doing. But you want to wait until you've actually drawn the free body diagram to start thinking about statics or dynamics. You don't want to worry at this point what you expect to be true, because your goal is to just define the contact points and those forces at the contact points, as well as any forces due to gravity. Okay, so we have now the free body diagram of our cat walking on the beam. Now let's suppose that this whole thing was set up by an evil 8-year-old who has a string on the brace. The evil 8-year-old, this is the evil 8-year-old, pulls the string, the brace falls, which causes the beam to fall. And so now, sadly, our cat is falling upside down. Okay, well, again, let's try to find a free body diagram of the entire cat that's falling. If we go back to our sequence of instructions, the first thing is to define the system. And in this case, again, we'll assume that the system is just the cat. The second thing is to sketch the system. And again, I will just copy my picture of the cat because it's easier than redrawing it. The third thing is, where has the system been cut from its environment? You'll notice that our cat really isn't interacting with anything in its environment right now. It's not standing on anything. It's not resting on anything. There are no strings pulling it up. So really the only thing to do is to locate its center of gravity, because the only force acting upon it now will be gravity. And then in step 4, we actually draw these forces. And again, the only force acting on the cat in this particular case is gravity. We're assuming that air, the resistance of the air is negligible. Maybe the cat's falling in a vacuum. Of course, that's not good for the cat either. But yeah, we're assuming that the only thing that's affecting the cat is gravity. So here again, we have a free body diagram. This is somewhat less interesting than our other free body diagram. It just shows that the cat has a force down on it exerted by gravity, which means in the absence of anything else going on, the cat's going to be accelerating downward. Now, because we want to end on a happy note, it turns out that cats, as I understand it, actually have a reflex that allows them to right themselves while they're falling, and by the time they hit the ground, unless they start too close to the ground or start with too much of a downward velocity, they can actually turn themselves upright, so they hit the ground upright as opposed to upside down. And suppose we wanted to start analyzing how the cat does this. Well, one way to do this would be to now start analyzing the different components of the cat and how they interact. Okay, so for this case, suppose we want to understand what happens with the cat's head. So in this case, our system of interest would not be the entire cat, but it would be just the head of the cat. Okay, so we would want to know perhaps forces and so on, what the motion of the head of the cat is as it's twisting itself around so it lands feet first. Okay, so step one would be to define our system, and in this case the system would be just the cat's head. Step two would be to sketch the cat's head, and I've already done that. Step three would be to define where our system, which in this case is the cat's head, interacts with the rest of its environment, which in this case is the rest of the cat's body. So we have this point of interaction. This is the point of contact. And then step four, well, and we also in step three need to identify the center of gravity. Since we're now interested in the cat's head, this would be the center of gravity of the cat's head. Then step four would be to define the forces acting on the cat's head. Again, we have a weight vector, which we might call W sub h, and we might have a force exerted on the head by the rest of the body. And in this case, where the head of the cat is actually connected to the body in such a way that the body can apply force as well as a torque, we might also have a torque related to this connection. Okay, so this represents now the free body diagram of the cat's head. Sometimes when you're working with systems like this, when you're trying to figure out how different parts of a system interact to do what they do, not only would you want to have a free body diagram of the cat's head, but you might also want to separate the cat's body into several different chunks, perhaps like this. And so we could then draw a free body diagram of the front half of the cat, a free body diagram of the back half of the cat, a free body diagram of the tail. The forces that act on the cat's head over here will be equal and opposite to the forces that act from the head to the body. So when we're drawing the cat's body as a free body diagram, we would have these same forces, but they'd be in equal, or they'd be in opposite directions. And we would draw the interaction between the front half of the body and the back half of the body, again as a force and a torque, and so on. And so by the time we're done, we might actually have 4 different free body diagrams. They're related by having several unknown forces and torques, and we could then use that to solve either a dynamics, in this case, since we want to figure out how the cat turns itself upright as it's falling, this would be a dynamics problem. Okay, so anyway, that's a brief introduction to drawing free body diagrams. One last thing to notice, when we're talking about how connections are represented between the environment, we typically draw forces and moments on the edge of the free body diagram. When we're talking about things like gravity, we draw the force or moment internally to the diagram from the center of gravity in the case of gravity. So in subsequent videos, we'll talk about different ways of figuring out, or different types of forces that you might encounter, and how to apply them to, or use them to come up with a correct free body diagram. So thanks for watching. I hope